Another question. 0.01 moles of H3POX, where X is unknown, is completely neutralized by 0.56 grams of KOH. Then X is equal to 3 and a given acid is dibasic from titration. X is equal to 4 and given acid forms normal salt. X is equal to 3 and given acid forms normal salt. X is equal to 3 and given acid forms acid salt. So either X is 3 or 4 from the options given. But we need to know whether it is a dibasic or forms normal salt or forms acid salt. So when we take 0.56 grams of KOH that is required for complete neutralization of 0.01 moles. So this 0.56 grams of KOH having one OH group with N factor as acidity is 1. The number of equivalents of KOH is given by weight by equivalent weight, and equivalent weight of KOH is nothing but molecular weight itself. That is potassium 39, hydrogen 1, 40 plus oxygen 16, 56. 0.56 by 56 is 0.01 equivalents. And for potassium hydroxide, 0.01 equivalents is nothing but 0.01 moles. Since this 0.56 grams of KOH is completely neutralizing 0.01 moles of H3POX, we need to understand that 0.01 equivalents of KOH can neutralize 0.01 equivalents of H3POX for complete neutralization. Therefore, 0.01 equivalents of H3POX will be completely neutralized to give normal salt. Now let us work with H3POX with either X3 or X4. If X is equal to 3, it becomes H3PO3 orthophosphorus acid. Now if we see the structure of H3PO3, where in all oxo acids of phosphorus being tetrahedrally surrounded, we have the structure for orthophosphorus acid as P double bond O, that is one oxygen is connected to central atom phosphorus either by double bond or coordinate covalent bond. One is the hydroxy group and another one is hydroxy group and then another hydrogen. So this is the structural formula where this particular hydrogen attached to central atom phosphorus gives reducing character. Whereas these two hydrogens which is connected to oxygen rather than to central atom phosphorus, similarly this hydrogen, these two hydrogens give basicity and thereby N factor for this acid, that is basicity, is 2. Thus when it is neutralized by 1 mole of KOH, one hydrogen will be replaced to give HO, P double bond O, and this H will remain same and this will become O minus K plus and water. Now it is indirectly H plus being replaced by K, it will become KH2PO3. But this has got still one more hydrogen to be replaced, therefore it is called acidic salt. In other words, when we use 0.01 moles of this, 0.01 moles of this will be neutralized to give acidic salt. So if X is equal to 3, it gives acidic salt. Now if X is equal to 3 and given acid is dibasic, so it is wrong. And if X is equal to 4, we have not checked. X is equal to 3 and given acid forms normal salt. If X is equal to 3, the given acid is forming not normal salt, it is forming acidic salt. So we have here X is equal to 3 and the given acid forms is acid salt. So this is the right option. But what about X is equal to 3 and given acid forming normal salt? What about X is equal to 4 and given acid form normal salt? Now if we add 2 moles of KOH, this particular acidic hydrogen and this particular hydrogen which are responsible for acidic character will be neutralized and we get a normal salt K2HPO3. This hydrogen is which cannot be given in the form of H plus as it is being directly attached to central atom phosphorus. This is normal salt. So if normal salt is to be formed, we require 2 moles of KOH. In other words, in the problem 0.02 moles could have been used, but we have only 0.01 moles. Therefore, this option C is wrong. Now X is equal to 4 and given acid forms normal salt. If X is equal to 4, the acid becomes H3PO4, orthophosphoric acid, which will have the structure of tribasic acid. And if it is to be completely neutralized, we require 3 moles of KOH to give normal salt. In other words, every 0.01 moles of this could have required for complete neutralization 0.03 moles of KOH. But we are using what? 0.01 moles. Therefore, acid salt will be formed. But what is given? Normal salt is formed is given. Therefore, B is wrong. So the answer is D.